So one thing to keep in mind is that we are going to be recording this. We'll be posting it online and sending you a link in a week or two so that you can view it or hand it along to others if you want. So this is recorded. If you're having any issues, we ask that you email Dory. Her email address is there, or you could give us a call on the phone, and her extension is 210. She can help you work through any of that, but hopefully if you're here, you're not having any issues. And a bit of an agenda. We're going to try to talk for about 45 minutes, and then I'm going to give you about 15 minutes to have a Q&A to pepper me with any questions you have, either on methods that we might have shown, how we do things, or potentially anything else that we might have talked about that you might have an interest in. So please, if you have a question in the middle, please feel free to put it in the chat. I will try to keep an eye on that, or raise your hand and I can call on you if needed, but there will be some time at the end, and looking forward to interacting with you all. So just one slide about me and Veryst Engineering. I'm trying to keep that to a minimum. If you don't know, Veryst Engineering is a small technical consulting firm located west of Boston. We work in a few areas. We do failure analysis, multi-physics simulation, and testing and material modeling. So failure analysis can be failure of conventional structures like large boom trucks, cranes, things like that, to very tiny polymer medical devices. Multi-physics simulation includes solids, fluids, heat transfer, fluid structure interaction, optics, low-frequency EM, chemical reactions, and a couple other physics that I'm not thinking about. And then the solid mechanics as well, which is where I focus. And then we have a test lab on site that's focused on characterizing the mechanical response of polymers, specifically to then take that data and select material models and perform finite element simulations. We test and model polymers daily here for finite element simulations. Not to toot my own horn, but I don't think you're going to find any better group than the group that we have here to design a custom test plan, understand your material, and get you the data you need. A bit about my background. I did my Ph.D. in solid mechanics from Brown University, where I was working on a project related to large strain, high frequency viscoelasticity. And I've been kind of trying to work in that field since then. I do a lot of polymer testing. I do a lot of simulations. I do a lot of failure analysis. And I work in all sorts of codes. And a lot of the work you're going to see here today, some of it was done by me. A lot of it was done by other engineers of us working in a group. So there are definitely a bunch of people here at Veryst who contributed to this. But these are really test methods that we have developed over the years based on client feedback and what we saw going on industry and some challenges that we had and how we've overcome those challenges. So we want to talk about some of those capabilities. And the first question might be, what do I mean by small samples, which we're going to show multiple examples of, but why do I need to test those small samples? And a lot of times we get a little bit of pushback from clients at the beginning that says, why do you need to test this? It seems like you're going to a lot of trouble. Why can't you just do a normal test? Why can't you use this other material? What's going on? Why are you doing this? The first answer is that sometimes that's what we have, right? A lot of materials that we get are very thin and small. So for example, polyethylene films are used extensively in batteries. And ePTFE membrane, so that's expanded PTFE, are used in a lot of medical devices and consumer products. And these are all manufactured by extrusion. So you take these materials, you put them through some rollers at high speed, you squish them down, you extrude it out. So that stresses and yields the material already. It's just like cold working, a steel beam or something like that. And so the material properties that you get at the end of that film depend on that manufacturing process. So how they're extruded matters. So we can't just take a larger, thicker film of this ePTFE or PE. We need to use it as manufactured, because even testing a film that's 3 microns versus 100 microns made by the same company will have different properties, because those properties are dictated by how they're extruded. Another one that we've done with clients, and is a good example, is solder materials. So the way a solder forms based on the kinetics of the cooling when the solder ball or solder drop is created. And so you can't just create arbitrarily large solder samples that then match the crystalline grain structure of your actual solder material that you're using in whatever PCB that you have going on. So you need to design your specimens to make sure that you get that same crystal structure and then test those specimens. All these solder balls that we talk about in our phones, laptops, electronic devices, your coffee maker at home, those are obviously, millimeters in size or smaller. And you're not going to be able to scale that up to a macro sample. So making sure you get that structure, and that structure plays a role in how the material behaves. So you need to make sure that you get that. Another one is that sometimes you just you don't necessarily have a good source of the material. We work with clients before where there's a seal that's made of a specialty elastomer that was specifically designed by company A to work in this environment and have these properties. And company B is using it and making a design, but they need to understand the material response. So to do that, we actually need to take the seal that material A, that company A made, cut it apart, create samples from that, and then test that, because we can't get a slab of the material or pellets or whatever we need of that elastomer. So we need to create small samples. If we're talking about a small seal, that's going to be a very tiny sample, and so there's some difficulties there. But that's another reason why we've developed some of these methods that I'm going to show you over the next 40 minutes or so. And taking another step back, you might ask, well, why can't we just use a standard? Well, most standards don't anticipate these kind of hurdles that you're going to have to overcome. And standards are really great. The standards organization, I'm showing ASTM and ISO up here. Those are two, one in America, one's international, but it's more European, I would say. But they both do great work. They have a lot of similar standards. I wouldn't say one is better than the other. But they're designed to be able to run the same test at multiple different labs and get the same result. And it's not to say that our test can do that, but it kind of uses standard equipment, standard methods, and then there's a 1 or 2 page document that you can create, say, this is how you test the materials, and then everybody can get the exact same thing. Also, a lot of times those are designed to be run by technicians who maybe need to run 100 or 1,000 of these in a row, and you do the same analysis, so you automate that, and then you're good. But as in those descriptions that I'm talking about, it doesn't really work. A lot of the standards say this is the minimum thickness for the material that you need, and we're well below that. So what do we do? And then the last thing is we always go above and beyond, because those standards are meant to kind of let people talk across industries, across companies, and give the same numbers and know that you're comparing apples to apples. But when we're doing this, we're doing it for a simulation. So we don't need to be able to compare apples to apples. We need that data to inform our simulation model to help our client update their design, build a better product, and get to market faster. So you're in this situation. You've got small materials. How can you kind of step back and make sure that you're doing the right thing and not making up the Sean Teller test that gives you absolute junk? The first thing is to use measurement systems just like you would use for all those other ones. You want them to have similar or better levels of accuracy. You shouldn't, unless you really need to, you shouldn't create your own new load cell. You should use a load cell that's available. Otherwise, there's a whole lot of validation that you need to do that. But really, we need to focus on strain, displacement, and force measurement, and making sure that we're scaling that to the appropriate force, displacement, etc., and go from there. And then for sample sizes, you'll see that we base a lot of our sample sizes when we have non-standard geometries on those standards. I was talking to a friend from grad school who has a similar background to me, and he put it better than I ever could. He said, our PhDs, our experience doesn't mean that we can ignore the standards, but we know why the standards were developed. We know why they're constructed, why they are, and that means that we can change them because we have a fundamental understanding of the mechanics that are going on, so that we can then change them to better suit our needs, but not reduce the accuracy or fidelity of any of our data. So hopefully I've convinced you that there are some instances where you need to use some small samples. So this first one that we're going to talk about is kind of the simplest one, which is smaller dog bones. So this has come to us from a lot of those examples where we get something of a manufactured part and we need to create a dog bone from it, but we can't get an entire standard dog bone. So we are, for whatever reason, we use the ASTM D638 Type 5 dog bone, which you can see over here on the lower left. This is the smallest size ASTM standard dog bone. There's a micro tensile sample. I have some personal issues with that. I don't understand. It's a little bit shorter, but it's a little bit wider, so it causes some other issues. But this is the one we work with, and all these dimensions that you see here are in millimeters. So you can see that the overall length is 63.5 millimeters. We're almost 10 millimeters wide. Maybe you're going to tell me, Sean, you could probably cut some of that off and be okay. And you're right, but we need a nice straight flat section here that's about 10 millimeters long and a little over 3 millimeters wide. And maybe we don't have that. So we've created two other dog bone size based on these, where what we've done is we've done like a half size for the length. So you can see here we're 31.75. The gauge length is now a little 4 3/4 millimeter. But we didn't scale everything else. So the gauge width is about the same, so it's 3.18. Then we scaled the tabs here a little bit as well. So those are 6.36, but the width is the same, right? So we have less material, but it's still kind of 4 to 5 millimeters, easy to deal with. So I meant to show this earlier. And if you're not familiar and you're having problems with the millimeters, right? This is the size. You can see my finger. This is a type 5 dog bone. So we're going about half that length with the same width. So then obviously beyond that, let's go, we did a quarter size, so basically the same thing. Here we halved the width, but we kept a little and half the length here. So overall 15 millimeters. So we've now made this, quarter the size of the original. So obviously you're gonna be like, well, how can you test this, Sean? Are you, do you have some extreme dexterity? And, maybe I used to, but we have some engineers who here are really good at this. So put together a little case study here on using these. My daughter isn't old enough to be using Legos yet, so I went to my friend's house and I stole a couple Lego bricks from his son, and we decided to pull them apart to test them because we thought this would be, everybody understands and has seen Legos before. So this is that half-size dog bone that we're talking about. So what we did is we cut off part of the face with a bandsaw, and then we were able to die cut these out from there. We chose something that was flat, so it was nice to start. But we had these smaller dog bones, and we're going to go through some results. Over on the right, you can see the machine that we did this on. This is a standard universal test frame. This one is from a company called ADMET, which is located here outside of Boston and Norwood. We have two of their machines here. We love using them. You can see a temperature chamber down there in the back. Currently, this one has fixtures in there for compression, and you can see an extensometer on there. But we're obviously going to do tension. And just to give you, a sense of scale, we have kind of mid-size, what I would call mid-size electromechanical load frame. This one can do 5,000 pounds or 22 kilonewtons. So not big, not small. I'd say that this is 18 or 20 inches across. I'm going to be mixing units here. I apologize for that. 18 or 20 inches across to give you an idea of the size. So the first thing we're going to do is talk about how we measured the strain. So we use a method called digital image correlation. So that's what you see in this animation here over on the right. So this is one of those actual samples that we talked about. And the contours on there are the strain contours that we calculate after the fact. So the test that you're seeing here is a cyclic test. So that's why you see kind of a pause here. But you also see in the background down here, there's a speckle pattern. So that's a random black and white spray paint that we put on the surface. And that's what the DIC needs. And then we unload, we load up here. We're going to hold this strain for 30 or 60 seconds. Oh, in that case, we went to failure. We're holding the strain for 30 or 60 seconds. Unload, reload, hold. And then you can see that there. So this can be really nice. This can be a good check to make sure you don't have any issues with the sample. You don't have any alignment issues. You can see that we have a little bit of a non-uniform strain field as we start to load up here. You'll see that we got a little more strain on this side compared to the other. That's one of the things I like about DIC. You can see some errors that you have, as well as you can see what we call localization or necking, where you see the strain. See if I can pause that. Nope. stop right there and kind of localize right before failure, which is typical for an ABS type material, which Lego infamously or famously uses in their bricks. Here's some static images. So when I send you these files, you don't just have a poor video that doesn't play in your PDF, but you can see some of those DIC images, right? So we can see the strain there. We see a little bit of that non-uniformity, a little bit of the necking, and then we have failure. So strain field looks okay, Sean, but what does that mean to me? So here's two results on samples from the same brick done at a strain rate of 0.01. We like to do what we call SMART or advanced testing here. So that's that cyclic testing where we go up, we hold the strain, we unload, then we reload. So you can see here we have two repeats. The data is pretty, these repeats look very similar to each other. The big difference is that, one of these failed at, we'll say 25% strain. The other one went to 70% strain. This is an N equals 2. I wouldn't put anything on this. Failure is a stochastic process, so making sure that you test multiple samples, if that's what you're interested in, would be important. You can see here there is a little bit of noise here, but with how small those samples were, they were 3 millimeters wide in the gauge section, and these are like on the order of a millimeter thick, right? This is not very much noise, so no issue, kind of with data fidelity or anything like that. And if you're not familiar with ABS, this is very typical material where you see necking and softening after the yield. You get that, and then a stress plateau. So I showed you 3 bricks at the beginning. So we tested, 2 samples from each one of those bricks. So you can see 6 repeats here. They're colored the same way as the Lego bricks are. So we've got the dark blue, the light blue, and the green, which I'd like to say I planned out that nice color palette beforehand, but I really just grabbed the first 3 bricks I could steal from this child. So overall, there's not a lot of difference between these two, which we wouldn't really expect. The stress plateau seems to be lower here on this light blue one. It's hard to say if that is a material difference. I have no idea what these bricks have been through. I think they were bought at a thrift store. So these have been through how many kids and how many UV cycles, we don't know. And one of these bricks could be 5 years old and one could be 15. So in a real use case, we'd want to really know the history of these bricks, but again, you just see a little bit of noise in the force, but overall you're getting the same response. So that was an example where you don't have a lot of material. Maybe you're reverse engineering something or reverse engineering the material and trying to understand it, and you got to get a small sample out of something. So I talked about tension. I probably should have put compression next, but that's in a couple slides. So we'll talk about small compression in a second. But this next one I want to talk about is very thin materials. So I had mentioned things like polyethylene films and batteries, adhesives in consumer electronics, OCAs or optically clear adhesives in displays in AR and VR devices, as well as membranes in medical devices can be very thin. We actually recently did some work for a client doing tension on dog bones that were 3 microns thick, so very, very thin there. And so here we wanted to do an example. This one is a polyethylene film that we got that was 100 microns. And so this is really targeted at looking at like battery type applications because these types of films are used there fairly extensively. So we're going to do both tension and compression testing of this. So the tension here is, we're going to use our normal, this is a normal type 5 dog bone, but it's 100 microns thick. But then we're going to do compression in the through thickness direction, which is one of the more interesting things. One of the fun things is that, some clients are like, I can't believe you can measure forces that small. What do you use? So we have a range of load cells in our lab from 2.2 pound forces, which is just below 10 newtons. At this point, really up to 5,000 pounds. We actually have, we used to have another machine from Instron that had died that we could do 50 kilonewtons. It wasn't something that we needed a lot of, but we used to have those even larger ones. But we go from 2.2 pounds all the way up to 5,000 pounds, and we've got 10 load cells or so in that range that we really choose based on the application, what the force that we need is. So Tension testing. So we did tension testing here at 4 different rates. We're going to talk about strain rates in a second. Um, but we did this at 4 different rates. In this case, we used a 100 Newton load cell to test these. Again, using that DIC. We went to much higher strains here. Polyethylene famously kind of goes to high strains before failing. But these are, I love these curves. They're beautiful. They're so smooth. If I showed you this, you wouldn't expect that I was testing 100 micron film. You would think that I'm testing a normal material, 3 millimeters thick, all that kinds of thing. So again, testing thin is not an issue. We've also done these at high rates, which we can do on our drop tower. We don't have any data I can share with that, unfortunately, but we've got the material, we got the capabilities to test these at higher rates as well. But this might have been the easier one. You might be saying, Sean, I understand going thinner when you're doing intention isn't that much difficult. So what about compression? So this is a fixture that we've developed over the years, actually based on some high rate data, which I'll show you later. We wanted to be able to do the same thing at low rates in compression. So this is how we test thin films in compression. So actually, we're going to start over on the right. So over on the right shows the actual fixture down here at the base, and then the samples. So we've created 3 discs of material. So again, these are 100 microns thick. I think these ones are 6.3 millimeters in diameter. So we put those 3 on these 3 pedestals. And then coming up from underneath, we have this little, it just looks like this round thing here. This is actually a non-contact displacement sensor. So we put these 3 samples, we have this fixture. It gets placed on these aluminum plates, which are really just there so our sensor has an area to go through. These are steel plates, excuse me. So just somewhere where we have those to go. And then on top, we take another plate that has a very fine surface finish that sits on top of there. We have a ball. That ball there is just to make sure that we're loading everything evenly as we go through the load. And then we apply the force from above. Again, this is done on that same electromechanical load frame that I showed earlier. These are the normal compression platens that we would use. And then we apply this displacement. So that displacement sensor, depending on which one we use, and a couple things that go into the math, but we have less than 0.1 micron. It's down to 0.02 microns of resolution displacement for this sensor. Another thing we really like about the sensor is we can use the same thing at like a meter per second, and there's no lag. It's a high frequency response sensor. So it's a very accurate, very, very fun for us to use. So one thing to note is that we do this loading. Right now we place this mass on there, so we like this with stiffer materials, not softer materials, because they need to be able to. We want the stress just from this laying on there to be very small. So here are the results. It can be tough with these stiffer polyethylene materials to go to very high strain. So in this case, we went to about 4% strain. The other thing you should keep in mind is that essentially each one of these lines is an average of 3 samples because we're loading 3 samples at the same time. Right? We're loading all 3 of these samples at the same time. So the force is distributed between the 3 of them, and then the displacement is the same for all 3. So each one of these is an average of 3 samples. So this really means that we've tested 9 samples. And you can see that there's a little bit of variability, but not too much noise. There's a little bit of waviness in the stress and the strain, but not a lot. The other thing to keep in mind is that 4% strain is 4 microns of displacement. So we've only compressed this thing to 4 microns of displacement. We're about 15 MPa. So there's a little bit of variability between these 3 samples, but given kind of our given hopefully what your expectations are for testing something 100 microns thick in the through thickness, that's a pretty low variability there. And then if we look at all the data together, you can see here that these look pretty similar. I don't have a zoom in here, but there's not really any difference in the slope here at the small strain, which is something that you might expect for these films because these are extruded. But in this particular film, we did not find that there was any anisotropy in the film due to testing in different directions in plane or in plane versus through thickness. Excuse me. Um, so next, I'm going to talk about a different class of thin materials at high rates. We're going to be talking about foams here. Um, but first, the question might be, why do we need to test materials at high rates? Why do we care about high rate versus low rate? So if you're not aware, almost all materials, and in particular polymer materials, are viscoelastic, viscoplastic, and that means that they have rate dependence. And I could talk for hours about where that rate dependence comes from, what it means, where you might expect it. Um, but but I think this is a good example on some nylon data that we tested. Right, all of these are done at 3 different rates. This blue is done at 1 times 10 to the minus third strain per second, and this purple is up at 150 strain per second. Right, so you can see there are 2 big things that change. You can see kind of the behavior here below 10% strain. Right, we've got a much higher yield stress as we go to those higher rates, and this material became more brittle at the higher rates as well. And so if you weren't aware, that is something that you want to think about when you're designing your test plans. If you're doing things at impact rates, you want to make sure you get some data up there. If you're doing things very slow, you want to be in that right ballpark as well. So you might be saying, Sean, that's one data set. Here's 4 data sets that we have internally on our own data that shows the yield stress as a function of engineering strain rate. So you can see all of these, have an increase. You just the x-axis is in the log scale, the y-axis is linear. So you can see that you're getting increase in yield, and sometimes you get some unexpected behavior where you see a transition at the higher rates. So that's why we need to test at high rates versus low rates. So I want to introduce you to what we call our thin film test machine. So this machine was developed over years to test things like foams, adhesives, including PSAs and OCAs, and other soft materials at high rates. Excuse me. We often test materials down to 50 microns thick, very high resolutions, 0.001 microns. We can't test thicker materials. We can test materials up to about 5 millimeters thick if we need to. But if we're getting that thick, it might be worth it to go to one of our other machines. And we can test in multiple modes. So it's currently set up for compression. So the testing all happens down here on this end. So this is a dynamic load cell. This is a non-contact displacement sensor. And then this is our compression platen. And all of this is just to make that thing move. So this is a pneumatic cylinder. We can pressurize it on either side and then release that pressure, and it shoots our piston either to the left or to the right to load the sample either in compression or tension or shear to the right. So right now it said compression platens are pretty easy. We have some kind of weird fixtures that we can use to grip adhesive specimens and pull them apart. I don't want to go into that today because we're really going to be talking about compression on these thin materials. So I'm going to show some data on a foam material that we tested, and I believe this foam material was a little on the thicker side. I think it was 400 or 500 microns thick. So on some of the other things we're talking about here, this is pretty thick compared to the 3-micron film I mentioned earlier. But this is the stress strain result for these on this machine, from a strain rate of 80 second in compression to 1700 per second in compression. I think this really shows one of the reasons why, particularly in foams, you really want to pay attention to rate. Foams have interesting behavior generally, right? If we start over here, they have kind of a linear or a pseudo-linear region, and then you get a stress plateau, which kind of looks like a yield behavior. And then as you follow that over here, at very large strains, you get what's called compaction. So this is basically when you pushed all the air, if these are open cell foams, you pushed all the air out of the material, and you're really starting to load whatever this foam is made of. I think that we did a urethane foam here. Whatever this urethane foam is made out of. And so really you're starting to get the compressive modulus of the urethane foam. And so it's just so much stiffer here, right? 200 MPa versus 0.5 MPa here at 4 or 5% strain. So here we did test it for rates. One downside of the system is that some of the lower rates we can't get to the really high strains because the rate is tied intrinsically to the pressure that we applied and the energy that we put in the system. So we were only able to go up to about 15% strain at this lowest rate. But at these other higher rates, you can see that we're getting compaction up to 70, 80% strain. Um, and you see a couple effects. The compaction here is basically on top of each other, but you have a different small strain response where you're getting stiffer and stiffer. That plateau stress increases. If we look at 15% strain, we're up here near 1. We were down here near 0.6. And then we're all the way down here at maybe 0.3. So in a couple of decades of strain rate, you're seeing, almost a 10x increase in kind of that stress that you would expect at 10%, 10 to 15% strain. And so the rate dependence here is important. Being able to test these small foams is important because you may not be able to get them thicker, or depending on the manufacturing process, their properties are going to change with the thickness. Some of these foams have what are called carrier layers on either side, and the carrier layers might be 10 micron thick polyethylene or polypropylene or something like that. So, a foam that's 50 microns versus 200 microns is going to have those same carrier films. So in the average sense, you're going to have more of those backer films in the thinner materials, and you're probably going to see a stiffer behavior and quicker compaction. So making sure you test your right thickness is going to be very important. So this one here, we're changing tracks a little bit to not just kind of straight mechanical tension compression type tests. This is something that we've been doing recently for some of our clients, where we really care about friction between very small things. So excuse me, I seem to be missing a slide. The question is, why do we need to test? I think I know where that is. Sorry. Why do we care about testing friction between small things? Well, in medical devices, industrial equipment, manufacturing processes, a lot of times you might have small things that are sliding past each other and rubbing up against each other. And maybe you're getting a failure in line, and it might be related to the friction and that rubbing that you're getting. So understanding the friction coefficient is going to be important. Maybe you need to look at good versus bad samples, good versus bad lots, etc. But maybe troubleshooting really depends on understanding the friction. You might say there are all these friction standards, we can just use those. But if you're using a small wire that's, say, 1 millimeter in diameter, or say you've got a injection molded manufactured part that has some complex topology, and is very small. Maybe we got a cross-sectional area of 1 millimeter that rubs up against something, and that's what you need to test. This is why we've developed that fixture for there. Also, a lot of times it depends on the surface finish, so you want to make sure you test your as-manufactured parts with the molds you use. Sometimes there's post-processing, whether that's grinding, abrading, blasting, lubrication, plasma treatment, heat treatments. All those types of things can change your surface finish and then change your roughness. So in these cases, really the only way to do this is to test those manufactured parts against your surface that you need. So this shows an image of that. You can see that 1 millimeter diameter wire. So we're testing the friction of that wire along this block of, I think, acrylic. And we really want to get the friction force. Right? So you might be looking at this 1 millimeter, Sean, can you really test things that small and get a clean signal? And my answer is yes. So this is the fixture we designed to do that. I'll walk you through how it works here on a broad scale, and we'll do a video on the next slide. So essentially, we have a lever arm here, and the lever arm has a basically friction-free pivot joint. It's very low friction based on our design. These two bolts are here so we can add mass. You can change the normal force. This big block here is a 3-axis load cell, so it measures the load vertically as well as 2 shear forces in this and this direction. That's attached to this plate, which slides on these linear rails that we can then pull over here. So in my opinion, the beauty of this design is that we're measuring the normal force and the friction force throughout the entire test before we get any of this motion. Right? We're measuring the friction, if I go back a slide, between this surface, and this right here is our load cell. Right? There's nothing in between here to add any drag from those linear bearings. We don't care how good those linear bearings are. They just need to keep us on track and make sure we're going in one direction and keeping things perpendicular. So as I said, it's a 3-axis load cell that's 10 newtons. So here's a video of the test. I think this is on a is on a slightly different material. We're moving at about 1 millimeter per second. If you focus here, you can see the model number of the load cell that we're using from Interface. Interface is a company that makes load cells in Arizona, I believe. No, I don't know where they are. Anyway, we use them. They're great people to work with, so we recommend them. But anyway, you can see that motion. We're just sliding along there. So Sean, the test looks good, but what does my data look like? So this is a plot of the force from one of these friction tests, and this is the orange line shows the normal force, and the blue line shows the frictional force. So I've tried to point out here kind of what's going on. So we start the recording, and then we take that lever arm and we put it down in contact to apply the normal load, and that's this jump, right? So we've got a normal load here of, we'll call it 1.2 newtons. You see a little jump in the frictional force measurement as well, which makes sense. There might be a little angle on there. And then we'll say 5 to 10 seconds later, we actually start the machine. We start it moving. So you see the friction force increases, and then we get stick slip. And then we went here for, we'll call it 10 to 15 seconds. And then we could extract the normal force from that, right? So, this has been great for us. We've done a lot of macro friction tests with the sled. They work fairly well. There are always issues with them, but this data is cleaner than the data we've seen on the macro in our experience. We're getting rid of any of that other noise. It's just been phenomenal. And you can look at these loads that we're measuring. We're measuring this friction force is 0.2 newtons, a friction coefficient of 0.2. In a project for a client that we did, we measured friction forces from 0.05 or 0.06 all the way up to like 0.25. It's a great tool to measure these very tiny friction forces. I kind of prefaced this earlier. So this is some small cylinder testing. I'm going to go a little faster since we're only supposed to be talking for a couple more minutes. So we talked about those tiny dog bones, but what do we do for compression? So here are some samples of an elastomer material that we wanted to test that were extracted from another material. And again, it was a complex shape, and we did some grinding, cutting, die cutting, low-speed saws to get these out and get cylinders. So these are near 2 millimeters in size. So you can see very small samples. They're very hard to work with and play with. But can we get good data out of these? Of course, if I'm showing it to you, the answer is going to be yes. So here's tests on those small samples that we showed you. So they're about 1 millimeter thick, 2.5 millimeters in diameter, right? So this is very, very tiny. If I hold up my little ruler here, right? 1 millimeter is just, my finger is maybe, 15 millimeters wide, right? So these are just tiny. So you can see here, the test data though is very clean, very repeatable. Again, we tested at 2 rates. This blue color was at 2 decades higher. We don't see a lot more difference in the kind of the stiffness, but we do see a difference in the unloading and the hysteretic behavior of these two materials, or these materials tested at 2 rates. Excuse me. And I think our last example is testing thin wires. So just like the other ones, when we're talking about these thin wires, you're talking about things that have been manufactured in a particular way, and their manufacturing process changes how they behave. So some of the examples that we've done are for medical device stents made of nitinol. So that's what's kind of shown in the lower left. On the upper right, those are some electrodes. Catheter guide wires are thin like this. The lower right, that's I believe an optical fiber. We've done optical fiber testing before as well. So how can you do these? How can you test these? Because you need to test the as manufactured. So the answer is we just use our ADMET universal test frame. So here's a wire that's a 250 micron diameter wire. You can see here in this microscope image, right? It's a black wire. That's not that interesting to look at. But here it is in the grip. So it's that same 250 micron wire. We're using just screw grips here. We've clamped it in between there. And then in this case, to measure strain, what we do is we add fiducial markers. That's what these are. So we track these with those same video cameras to measure the strain in between here. The first question you might come up with is, can you go to failure? And the answer is not really. We test a failure. Failure typically happens at the grips, so it's going to be a conservative estimate of the failure. If you could give us lots of material, we could use a method with capstan grips, but generally our clients are only able to get 10 or 15 millimeters of this, and we need something like, 300, 500 millimeters, probably even more than that, something on the order of a meter to do one of these tests in actuality with the capstan grips. So, and that you could get failure a lot better. So these particular wires was a nitinol test wire. If you're not familiar, nitinol has a shape memory alloy, has a lot of interesting properties where you can to use that are useful medical devices. So it's both super elastic and shape memory, so it goes to very high strains for metals. And it has this interesting behavior where you've got these stress plateaus. So you load it up, you hit the first yield stress, and then the yield stays the same, and then you get stiffening. And what's happening there is you're getting a phase transformation in the material itself. And I always get this backwards, so I apologize. Going from the martensite to the austenite phase transformation. And then at this point, all the material has transformed. It stiffens up. And then as you unload, you actually follow a slightly different path. And then as you're going along here, you get the phase transformation back the other way. And then you can reload again. And then this blue one was tested to failure. So, particularly for nitinol wires, these types of tests are really critical because depending on how your wire is processed, these upper and lower yield stresses, which is what those are called, will shift up and down. They also change highly with temperature. Sometimes you call that the austenitic finish temperature, can tell you a lot about how the material behaves. But those, and it also tells you how you can affect some of these thermal memory effects. But testing those is something that we've done a lot of. So the last one I'll talk about is something that we've developed here ourselves, which we call benchtop frame. This is something that we developed to really be able to do really small displacements, small forces in a controlled manner, and we want really, really repeatable alignment. The Advent Universal test frames we have are great, but we're constantly taking things on and off. We use 8 different load cells. And we've got these fixtures on there that are quite large, and then we're constantly shimming things to make sure our alignment is good. But when you're talking about something when 1 micron matters a lot, or 0.1 degrees matters a lot, we wanted even more control with something that's really focused on these really small ones. So we developed this test machine. The first one is one that we developed and gave to a client where we did 4-point bending. Right, so this is maybe 12 inches across to give you an idea of scale. And then the one on the bottom is the one that we're currently building right now so we can use this in-house for our own. Again, this is all to ensure alignment. We're using interface load cells. This is an actuator we buy off the shelf. So here's some more images of the CAD. You may or may not be concerned. Be like, Sean, you're a testing lab. You're not a machine design company. We have engineers who do machine design better than I do. And additionally, a lot of these components, we've used the designs in our drop tower. So the drop tower is something that we designed 8 or 9 years ago and have been using since then. So we're really confident in how it behaves. Again, sample alignment and repeatability is what this is going after. This is a type 5 dog bone to give you an idea kind of scale, what's going on there. So a brief summary, the summary that I would say is that sample size and the amount of material you can get me does not limit what I can test and the value of the information that I can get for you. I can get clean, repeatable data that really helps you understand your material, even if it comes in a weird shape, form factor, it's very thin, anything like that. These are some of our capabilities. I think there are a couple that didn't quite make it in there, but we like to tell our clients, really ask us. We like saying no. We think it gives you value if we tell you we can't do it. Come to us with the question. We'll let you know if we can test it as you think, or if we can come up with a method, and we'll discuss any pros and cons as well as you with that method. So that's it. Just a little bit more advertisement. We're going to be continuing this webinar series into the new year. The entire schedule hasn't been posted. We're doing one a month. January 11th, we have It's not testing related. Introduction to Abacus Python scripting with my colleague Nick Vasios. Our CFD colleagues are getting in on the action. Joe Barakat is going to be talking about CFD and population modeling for mRNA vaccine production. We've done a lot of work there with mixing and turbulent flows. My colleague Scott Grindy is going to be doing high rate testing of adhesive March 14th. And then I have a couple courses that are paid both online and in person coming up. So I believe this one is on the website. The next two are not. My paid webinars are, and this one is not. But those will be coming in the coming weeks. And if you're interested, send us an email and we'll let you know when they're up. Not all of you have opted into our communications, so we try to honor that. But if you are interested, let us know, and we'll be posting things on LinkedIn as well. So thank you very much for taking the time today, and we've got a little over 10 minutes left, so I'm happy to sit here and answer any questions you may have and see if there's any way I can help you.
Hey, Sean. I can't find the button for raising my hand. I'm used to Zoom, but good to see you again. Great talk. That was cool to see some of that stuff that you guys are doing. I did have some questions for the thin film compression, that custom fixture that you made for the ADMET.
Yeah.
Are you guys concerned with friction between the sample and the platen for that, and concerned with barreling or any of that stuff, where sometimes, in the past we've tried to reduce the friction between the material and the platen? Is that something you worry about for those tests too?
Yeah, that's a good question, Greg. Yeah, we do. We try to lubricate. We may or may not go to very high strains because of that. Because as I know, Greg, and others on here might, the higher you start to get what's called a barreling effect, where you get a non-uniaxial stress state due to the friction between the platens and the compression. The higher strains you go to, the more error that is. By lowering the friction, that reduces that effect, but obviously it doesn't eliminate it unless you have no friction. So we will add lubrication in there. This 6 millimeter sample size, we kind of choose based on what we're trying to get. If we want to go to higher strains, we might go to an even smaller sample to get a better aspect ratio. And when we do this on foams, we don't worry as much about that because they have a much lower Poisson's effect, and therefore that effect is much less pronounced. So hopefully, so the answer is yes. I always worry about friction.
Yeah.
And good to see you too. In case you don't, for those who may not know, Greg used to work with us here at Veryst, so he's gone on to greener pastures. But he helped develop some of these methods years ago. So.
Great. That was awesome. And just, I guess, one other question kind of about that fixture. It's a really interesting fixture. I like it a lot. But controlling the ADMET to such small displacements, is that something that you worry about too? I mean, no. You said 0.4 millimeters is what you were displacing?
Yeah. Not really. So there cyclic tests can be a little harder to control. If you want to hit 5% strain exactly or 10% strain, that can be a little difficult. What we've found more useful in these thin films is that we can control the ADMET in a way that we say move at 0.001 millimeters a second until the force is 1,000 newtons. So we'll go at a displacement rate, but then we stop at a load and then unload to a load and that kind of thing. The other thing that we've done, which we didn't show here, in some cases when we want to go really slow, is there's more to this fixture where it gets put on this large structure with the big spring. And so essentially we have a spring in series, and we tune the spring based on the size of the samples so that the spring gets most of the deformation. So that way you're lowering the deformation rate on the sample. But the force is obviously the same. So we've done that as well to in a similar way to go even slower.
Very cool. Thank you for explaining that. That's cool.
No problem. And then I saw a raised hand from I'm going to butcher your name, so I apologize, Dr. Tagza. Tagza. Let me see if I have a message here. Oh, I do. Let's see. Oh, there two. How do you determine the thermal pre-soak time before testing at non-ambient temperatures in the chamber? Um, so thanks for the question, Mitch. So we generally, for most materials, we just want to make sure that we are at equilibrium. So for the material itself, we'll want at least like 20 minutes in the chamber and then a couple minutes in the grips after the door is closed. That said, you need to be careful and make sure you're not getting any aging effects. Sometimes with adhesives, the high temperature ages it and changes the properties. If you're near like a glass transition, you can like for things like PET, you can get cold crystallization if you're at too high a temperature, and that depends on the amount of time. So you need to be careful there. But for most materials, we want to make sure we're at equilibrium. So we'll give it a good 30 minutes. Dr. Tag is at, I know I pronounced your name incorrectly. I see your hand up. You have a question?
Thank you very much for your awesome presentation, and I learned and inspired a lot from.
Thank you.
What you presented here. Many thanks for it, and I have just a couple of questions for you.
Sure. I think I called out all that. You are breaking up a little bit, but go ahead.
Research. I'm researching on biomedical applications of the. I need multi-axial tests on biological tissues. Present something to have multi-axial tests. How is that part of the presentation? Did you talk about that?
Yeah, no, we don't do a lot of multi-axial tests. We had developed a fixture previously for biaxial testing on a universal test frame. It worked okay. It's not something I'd present because I don't think it's great. So I don't want to put my name on it and put it out to the world. We have done things like planar tension tests, right? So that's where you take maybe something that looks like this piece of paper, you grip it the entire top and bottom and pull, and that's a pure shear state with your material is incompressible. But I haven't done a lot with biaxial testing because we've had difficulties doing the testing. And then for most non-biological materials, there's not a lot of I2 dependence on the material models that we're interested in. So, and that materials we're interested in or the material models we're interested in. So we spend a lot of time and effort to measure something that doesn't impact our simulations. That's not true for biological tissues. So, I mean, I think you're right. But I know ADMET makes biaxial tension frames. I know others do as well. I know there are some designs out there, but to me, it becomes a specimen design issue as well as a control issue, which I am not an expert in, and kind of control systems.
Very good, very good. Many thanks for your explanation. And just one more questions for you, and that's all. What kind of motors you're using in your setups?
In our kind of universal frames that we bought from ADMET, I don't know. It's electromechanical. That's why we buy it from them. They know what to do there. In the benchtop frame that I showed somewhere here, I think. Oh, there we go. Oops. This one we got from PI Physics Instruments, which is a German company. It's a piezoelectric actuator, very small displacements, very well controlled. You might be able to get something similar from like Maxon, but this we've worked with them before and we like theirs.
Thank you very much. I won't take much more your time. I will ask you a couple of more questions on your LinkedIn account. Thanks you very much for your explanation.
Yeah, thank you. Let's see, I've got let's see, I got one. Let's see, it's from Isaiah says, can you explain some of the sample preparation methods or tools you use for soft or hard materials at different scales under compression and tension? So all the dog bones that you saw here, we used die cutters. So we, steel ribbon die cutters. So the Type 5 is a normal one that you can get off the shelf from a lot of people who make those dies. And the ones, the smaller ones, we just provide a drawing to the same company and they'll make a custom one. So that's how we do the tension samples. We've also done things with like water jet cutting and machining, but machining these very tiny samples can be difficult. And we'll do that both for things like ABS as well as like a soft elastomer. They provide different problems. With ABS, we've got a nice big manual press that we can use to cut through things that are stiffer and tougher. For the really soft materials, we'll actually attach samples to a flat plate on a lathe and put a die in the lathe chuck and use that to cut the sample to get a nice uniform sample. Otherwise, it's careful work with a slow speed saw and really some grinding operations and putting things in kind of fixtures to make sure you get sides parallel and flat. But for some of these things, the method that we found works best is kind of these manual operations. And if you need 10 samples, you create 20 and you choose the best 10 because we found it's easier to create more and choose the ones that turned out well as opposed to spending an hour and a half to cut each sample by hand. Okay. Well, unless there are any other questions or I missed any or you need me to add anything else, I'm gonna call it a day. You'll be getting an email from me in the next week or so with kind of handouts from here, as well as a link to the recording and our next couple webinars. So take a look out for that. You'll have my email then if you don't have it, but please feel free to reach out either on LinkedIn, through email. Always happy to talk with people, and thank you for spending some time with me today.